if you, I didn't have anything planned. I just wanted to have some time for questions, if you have some, or if you want an overview, or how can I be of service? Got paper, ruler, compass, calculator. We can do some calculations if you want. I mean, really anything.
I guess I'll just ask quickly in your response to the well, no, actually, the last question where you asked, is there any reason why astronomers might not believe or Kepler's proof that it's not that the orbit of Mars is not a circle but it's rather oval? Is there any reason? I mean, I thought that unless they were just refusing to think and they went through the actual arguments, that they would actually believe him at this point in the book. But I'm not really well versed in astronomy. Is there any actual legitimate reason why astronomers might not believe Kepler at this point, that the orbit is an oval shaped or not circle at least?
I can't think of any. I mean, it's so compelling. Because what does he put together? He's got, I mean, he's got the distances. So he's got these. Put it up on the picture up here. Hello, probably nobody. I don't know if anyone can even see that. It's kind of small. There we go. And so I mean, he's got these distances of the planet. I mean, first he measured the eccentricity. He knows he feels very confident in the distance
right.
of the Sun and the center of Mars's orbit. One thing's for sure is that the distance to these 2 points is absolutely certain. He feels very confident in the distance to epsilon and the distance to delta. And taking the average of those distances as the radius and spinning it around, he gets where these other points should be. They're definitely closer than that. And he's very certain about those distances. I mean, it would be very hard for anybody to complain about him. Also because he got those 3 distances using different techniques in part 3. To make it real clear that the Earth didn't move in the eccentric everybody thought it did, he used different techniques to look at its orbit, using the mean sun, using the apparent sun as the basis, with and without the vicarious hypothesis. So it seems pretty indisputable. The thing that he does in chapter 43 would probably be less compelling. The thing about why the planet's speed. When he uses his area time as a way to approximate the sun's power on the planet, it goes too slow on the sides, and he says that's before squeezing it in. People may or may not agree with that if they, really dislike his physical theory idea, but the distances really make it indisputable. I think that's why he brings up Copernicus's epicycles, because people might say, okay, maybe it doesn't move in a circle. Maybe it moves in a combination of circles. So, and the one, I wouldn't say famous, but the one known example where the planet moved in a combination of circles, besides Ptolemy's huge epicycles, was Copernicus and Tycho Brahe. They didn't use equants, they used 2 very small epicycles to make the planet speed up and slow down and have an eccentricity. And that actually makes the planet come out farther to the sides rather than coming in. So, unless there's some other things people might come up with, it's really clear it comes in at the sides. Although, ironically, what Kepler's about to do in chapter 45, he's about to make the planet move with a combination of circles. So
Oh, really?
that's going to be
Huh.
his first type, because basically, I mean, after this, he's like, okay, well, we got to do something now. If the planet's moving in and out, I got to make some hypothesis for making it move in and out. And the one that he comes up with it's kind of hokey. It uses an epicycle to move the planet in. Okay. You know, he's got the power of the sun's moving it around, but what's going to make it move in and out? So, for that, we'll cover this again in the next one, but just to say what his hypothesis is, he looks back at what he'd done in chapter 39, where he says, if you wanted the planet to move in a circle, an off-center circle, this epicycle would have to twist at a differing rate all the time. So Kepler's first hypothesis to make the planet move in and out is to put the planet on an epicycle
Mm.
that rotates at a constant speed. So if you watch this epicycle here, and watch where the red point moves, if let's say noon is that gamma, so it's at 1 o'clock, 2 o'clock, 3 o'clock, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the epicycle rotates uniformly, and because the planet, is slow at aphelion, the epicycle spins a little extra and brings the planet inwards, and then it catches up by perihelion. See right there. So that's the idea that he's going to come up with in 45, which after, proving that there's no epicycles and equants, again, kind of like when he brought the equant back in part 3, feels a little bit weird. Like, what were you thinking, Kepler? You brought in an epicycle? But it's easy to say that. It's harder to say, well, what should he have tried? So he's going to try this out, and then it's going to fail in a specific way that gives him a big insight later in the book to figure out what does make it come in and out. So if he hadn't tried out this funny idea, he might not have ever come up with the answer. Try something, see how it works. For people who just got on, this is just it's open questions, no particular presentation for me here tonight. Including specific ones, like we can do calculations together if you want. Maybe you can see it. There's that view with the ruler and the calculator. So whatever would be helpful.
Sounds good.
Okay.
Are we shifting to another question now, or?
Was that good, Hector? I wasn't trying to cut you off. I figured that was.
Yeah, that was good. Thanks.
Okay. Well, floor's open then. Yeah. Are you trying? Cameron, if you're trying to talk, you're muted right now.
Oh, I was just pulling up the homework. I did have a question. I just have to find it in the homework.
Okay. It doesn't have to be part 4. Well, yeah, Cameron's looking for that, but just so everybody knows, I mean, this anything's fair game.
Okay, I found it.
All right.
I was stumped on question 4 from part 3. What does Kepler determine the difference to be between a model based on his physical hypothesis so far and the equant model, looking for a quantitative answer? So I found out that I think the other model that this question is referring to, as far as Kepler's physical hypothesis, is an area time model. I don't know if that's true, but just how to get the... I was just confused on the question and how to do the calculation, because I don't even know. I think I figured out what the question was, but it was just a little ambiguous.
Was that a question from the second part of part 3? Like that was the last question for part 3? I haven't looked at all the homework. See, is that where it was? Cameron?
Sorry, it says from session 2.
Okay, and the question was, can you read the question again?
Yeah. It says, what does Kepler determine the difference to be between a model based on his physical hypothesis so far and the equant model, hint, looking for a quantitative answer?
Oh. Well, he does it on, it looks like it's on page 422 in chapter 40. He, what's he doing here? Yeah, it seems if you look at that first full paragraph on page 422, he says, so just to give the background on that, I think what he's looking at is he's looking at the area of the hold on a minute here. Oh, okay. Yeah, he gives it. It's right there at that first full paragraph on page 422. He's describing now. He's comparing what he had done. Here, let's start at the bottom of page 421. At that very, very last line. Well, okay, a few lines up from the bottom of page 421, Kepler says he's looking at the area of the circle, and let me switch that. He's looking at the area of the circle. And he says, so the area BEA has a value of 1 degree, 1 minute, and 53 seconds. But in chapters 29 and 30, the angle BEA was also 1 degree, 1 minute, and 53 seconds. Therefore, both parts of the equation are equal at this place, that is, near 90 degrees. So, and just to go back to what he's comparing this with, and let's look back. In chapters 29 and 30, he's using this bisected eccentricity, and he's basically remaking the table for the. Okay, because what's the context for this? Kepler opens up part 3, showing that where people thought. If you switch over to the viewer that you see that calculator on, I'm going to do a drawing. So switch over to that view if you're watching on the live stream, and it'll change automatically on YouTube. So what everybody had thought before Kepler was that as far as the Earth goes, this is what Copernicus said. We got the sun, and we've got the Earth. The Earth moves in a circle, not centered on the sun. It moves on a circle over here. There's its center. What Kepler had shown was that this wasn't really the center. So let me just write this. So this is center for Copernicus. And the distance between the two here is 3,600. That's the distance between the Sun and the center of the Earth's orbit. What Kepler found was based on finding specific distances of where Earth was. So, in these different chapters, you would find a few different spots where Earth was by keeping Mars standing still. He drew a circle through them. And the center of the circle was right here in the middle. So this is Kepler's center. And this is Kepler's equine. So the the difference between those two models there is not that big because the eccentricity is small. So what Kepler is doing in chapters 29 and 30 is saying, okay, using this bisected eccentricity, where is the Earth, where's the Sun and the Earth going to be? He makes a table about it. The reason he does this is because he's just changed the solar theory, and what he does in the very next chapter 31, is he says, what's the title of 31? That the bisection of the Sun's eccentricity does not perceptibly alter the equations of the Sun set out by Tycho. Because people would object. They'd say, Kepler, what are you doing? Tycho's solar table was perfectly fine. There were no errors in it. You've just introduced a new theory of the Sun, or the Earth going around the Sun. So obviously, you must have changed what wasn't broken, what worked. And if you changed it, your thing must be wrong, right? No. He goes through in chapter 31 and he shows how incredibly small the difference is. So he says in chapter 31 on page 370, he says, what's the number that he gets? Where is it? I'm not seeing it all of a sudden. I'm not. Maybe what I thought was in this chapter isn't. Hmm. Oh, he says da da da. Oh no, he does give an example. Yeah, it's correct. On page 370, right in the very middle, he says that the difference between his technique and Tycho's technique makes a difference of 4 seconds. No one's going to observe 4 seconds. And then he gives another example where it's, it's similarly small. It's on the order of seconds. So, so he's saying, hey, okay, you know what? This isn't changing things dramatically from Tycho Brahe, so, no worries about it. The rightness of Tycho Brahe's predictions don't mean that he's wrong, because he gets the same numbers, basically. So then, on that homework question, is asking you to look at chapter 40 and figure out, now that Kepler's using area time instead of this bisected eccentricity with an equant, how does that change where the planet is observed? And the answer appears to be on page 422. So again, starting at the very end of 421, Kepler says, the area of this circle is to 360 as the blah, 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 blah. So he gets 1 degree, 1 minute, and 53 seconds. So the area BEA is 1 degree, 1 minute, 53 seconds. But in chapters 29 and 30, the angle BEA was also 1 degree, 1 minute, and 53 seconds. Therefore, both parts of the equation are equal at this place, that is, near 90 degrees. The reason it's exactly the same at 90 degrees, I'll switch over, I'll draw this, is that the physical, look at the two different anomalies with a, hopefully you can still hear me okay. Okay, that didn't show up. Here's the sun, here's the center, and then optionally, here's the equant. When Kepler compares the two different ways of figuring out where the planet would be, one would be, Kepler says, let's make the eccentric anomaly be 90 degrees. Now, if I used a bisected eccentricity, the question would be, where does the equant see the planet? What would this mean anomaly be? Or, what's this angle? In the bisected eccentricity version, this angle would be the physical equation, the difference between the mean anomaly seen by the equant and the eccentric anomaly seen by the center. In the area time model of chapter 40, this area would be the physical equation, would be the difference between the eccentric anomaly, which is 90 degrees, and here's 90 degrees worth of the area of the whole circle, and then the total area swept out by the planet, which includes this triangular area. So in chapter 40, let me just label these. So this is chapter 40's physical equation, and this angle here this is chapter 29 or 30 physical equation. And remember, just as a reminder here, physical equation always means, you can count on this, is it's the difference between the mean anomaly and the eccentric anomalies. The difference between them is the physical equation. And so Kepler says at 90 degrees, it's the same thing. This angle here is 1 degree, 1 minute, 53 seconds. And the area of this triangle is also 1 degree, 1 minute, and 53 seconds as a portion of the circle. So let's read this again. He says, starting on the fourth line from the bottom on page 421, Kepler says, now let me write the letters on there too, so we can follow it more easily. Okay. He says, and as the area of the circle is to 360 degrees of mean anomaly or time, that is to 21,600 minutes, that's just 360 degrees, said another way, or 1,296,000 seconds, which is also 360 degrees. So is the area of the triangle, 90 million, to 3,713 seconds. That is to 1 degree, 1 minute, and 53 seconds. That's the area of the triangle. So the area, BEA, has a value of 1 degree, 1 minute, and 53 seconds. But in chapters 29 and 30, the angle, BEA, was also 1 degree, 1 minute, and 53 seconds. Therefore, both parts of the equation are equal at this place, that is, near 90 degrees. He continues, at the other degrees of eccentric anomaly, we proceed as follows. Since BEA is 3,713 seconds, he's describing the area of the triangle in seconds, where again he's saying the area of the whole circle. You know, minutes and seconds, he didn't have decimal points back then, so a minute is just a way of measuring something in terms of 60ths. So when he says the area of the triangle is 3,713 seconds, that's saying if the area of the whole circle was called 360 degrees, and we broke it up into 360 parts and broke those up into 60 parts called minutes, this triangle would be 3,713 seconds. He says, since BEA is 3713, as its altitude EB is to HL, or GM, on the picture there, the altitudes of the other triangles, that is, as the whole sign is to the signs of the eccentric anomaly, HBC or GBC, so is 3713 to the areas of the remaining triangles. And I'll draw this in a second. He says, so 3713 will be multiplied by the sines of the angles at B, and striking out the last 5 digits, the remainder will be the physical part of the equation expressed in seconds, corresponding to the angle at B. For example, let HBC be 45 degrees, 43 minutes, and 46 seconds, as it was above in chapter 31. Therefore, its sine, 71,605, multiplied by 3713, with the last 5 digits struck, gives 2659 seconds. That is 44 degrees and 19 minutes. In the table above, we assume this to be equal to the optical part of the equation, 43 minutes, 46 seconds. Okay, so let's go ahead and draw that out here on the paper. Switch over to that. So, I might have to redraw it. Let's see, maybe not. So here's H. I can just yell out if it's too much. I can redraw it. So what Kepler is doing now is he's going to take a look at this new triangle. He's going to look at the physical equation up at point H. All right. He wants to know, how big is that triangle? That triangle is so that triangle, just to redraw it here, we got this distance HL. BA. And we'd like to know its size. Well, the area of a triangle is half its base times its height. He's already done that for triangle EBA. So I'll draw that one on here too. The area of this triangle is 3,713 seconds. Kepler says to get the triangle HBA, here are his steps. He says HBA is, let me read it again. He says, where is this here? He says, well, first off, area angle HBC is 45 minutes, 43 seconds, 45 degrees, 43 minutes, 46 seconds. I'll write bigger. Sorry, I know that's too small. So he says, let's take its sine. HBA is, it's 3713 times the sine of HBC. So he says it's 3713 times, and then he writes this number. He says, where is it? He says it's 71,605. Let's go through how he got that. So, I think, let's see. Okay, I think you can. Is this sharp enough? Can you guys can you actually see the screen here?
No.
Oh shoot. Well, you know, I'm just going to type this in here. The sine of remember to remute yourself there. The sine of 45 degrees, 43, and I've got a calculator here where I can just actually put in a minute symbol. It's so convenient. 45 degrees, 43 minutes, 46 seconds. And I don't know if you can see the display, but it says 0.71605. That's how Kepler got that number. I got the exact same number with my calculator. Now, Kepler didn't use a calculator. He looked it up in a table. But that's where this comes from. So if we go ahead and multiply 3713 times 71605, and then Kepler says strike out the last 5 digits. I mean, cut off those last 5. And we get, because this is really 0.71605, we get 2659 seconds. Let's see what Kepler says. He says 2659 seconds. So we got exactly the same thing he got. 2659 seconds is 44 minutes and 19 seconds. But earlier, this is what Kepler had said. Kepler had said this is what the equation was from the earlier chapters. In other words, what Kepler had said was using the bisected eccentricity, what Kepler had found, here's what he really did. In the earlier chapter, he put another point here to be the equant. And from the equant, he went 45 degrees. He calculated what the angle would then be on the eccentric anomaly, 45, 43, 46. So the difference between the mean anomaly and the eccentric anomaly earlier in the book, in chapters 29 or 30, was 43 minutes and 46 seconds. Kepler just calculated the physical equation using area time to be 44 minutes and 19 seconds. So what's the difference between those two? See, if we had 14 seconds, we'll get to 44 minutes. So 14 seconds, and then 19 more seconds. 33 seconds. So that's the, I imagine that's the answer that Megan was looking for that homework question there. Let me come back over to the thing here. So the difference between where the bisected eccentricity model would see Mars and where the area time model would see Mars, 33 seconds difference. It's not very much. Definitely not within, it's not within observable magnitudes. With Mars, we'll soon see that it gets maybe it's a little bit different. So. Did you follow those steps? Did you have any questions about that part there, Cameron? About what I just went through?
It was a little fast, but I got the concept, I got the gist of it. This isn't being recorded, is it? Or is it?
Yeah, it is being recorded, yeah.
Okay. All right, I can look back at it. But yeah, no, I got the gist of it. Thanks.
Sure. Yeah. Just to say it one more time, Kepler is comparing those two numbers that he's looking at that I put in the box, that 44:19 and the 43:46. Those were the physical equation according to a bisected eccentricity, an equant, and then the physical equation using area time, where the physical equation is the area of that triangle. It's the area swept out by the planet in addition to the area that's just represented by the amount along the eccentric anomaly.
Detroit has a question.
Okay, shoot.
On page 457, a little bit down from the top, he says, "It thus happens that the distances of equal arcs on the epicycle..."
Oh, hold on a second, sir. 457. So this is in this is in chapter 45. Okay.
"It thus happens that the distances of equal arcs on the epicycle are accumulated near the aphelion C and the perihelion F, and are more sparsely scattered about the middle longitudes. we couldn't figure out what that meant.
Here, I'll show you on this. Let's get this animation up here. And then let me do this. Let me share this screen. I'll turn that paper into this screen so we can look at it. Okay. So if if you slipped over to that other view there, you can also see it. So let's. Okay. So this is the animation corresponding to what he's talking about. So the distances of equal arcs on the epicycle are accumulated. Let me just think about this for a second here. So Kepler's saying the epicycle moves uniformly while the sun changes what it does. The sun moves the planet more slowly when it's on high. It thus happens that the distances of equal arcs on the epicycle are accumulated near the aphelion C and the perihelion F, and are more sparsely scattered about the middle longitudes. In this way, all the shorter ones are drawn back upwards from the correct circular distances from perihelion to the place of the longer ones. That error therefore became rooted in me, which I had happily begun to refute in chapter 39, that it is a property of the planetary power to lead the body of the planet around in the path of an epicycle. I think I'd have to reread the beginning of this. I'm not really. I think I might have to get back to you on this one. I'm not really sure. The language is difficult to understand what he's saying here. Do you have any ideas? Do you have any idea what do you think he might mean by that?
Well, one thing that was a little bit confusing is which error he's talking about. Because we kept going back. When we were reading chapter 45, we kept going back to chapter 39, which we hadn't really worked through here. So we just kept getting like jumbled as to what he was hypothesizing, what his axioms were. And then when we would finally come back to 45, when he says that that particular error, I think we were also kind of getting confused on what he was talking about there. Well, but in terms of the accumulation, we couldn't figure it out.
I think the error that he's talking about is the error is the whole error of chapter 39. I think chapter 39 is where this is one of the animations from it. Chapter 39 is where Kepler he's finishing up part 3. He's got this power of the sun. And then he just takes a brief detour to point out how hard it is to make the planet move in a circle. It's actually really difficult to make a circle move. So he first off points out here that this might be repetitive for you, but I just wanted to go over it. If we watch this epicycle and look at what o'clock the black dot is on the epicycle, if gamma is noon, we see that the motion along the epicycle is very uneven as the planet speeds up and slows down. So let's count the time. So noon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, noon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So obviously very, very uneven. In other words, so the epicycle has to do this bizarre speeding up and slowing down if it wants to keep the planet moving on a circle. Kepler's still sort of believing that this blue dotted circle might somehow make sense, that there might be some planetary soul or something going on that's keeping him at constant distance from the sun. He doesn't really like that very much, but he says, even if we had that, how hard is it going to be to maintain the path on a circle? So he also shows that if instead of moving around the epicycle, it just reciprocates back and forth along it, that also is very uneven.
Yeah.
So he shows this picture of it, just that spot right along the diameter of the epicycle there. It's just there's nothing the same. That between gamma and iota is not the same as this. Everything's different. It's totally hard. So the general conclusion from 39 was, how is this planet supposed to move in a circle? It takes a lot of work. Circles seem really simple shapes, but it's really hard to make the planet move in a circle.
Especially with a reasonable cause.
Yeah, right. Yeah. I mean, because Kepler's even being generous, allowing these souls or whatever, some intelligence in the planet to try to think about things or whatever, things that we might say, I don't know about that. But he says, there's nothing, nothing works, and it's very important because this is going to come back in chapter 57, where he does have the planet change its speed to and from the sun. But there is a reasonable physical explanation for the amount that it comes in and out. With this, he says, the thing's basically going to have to carry around a table and do a bunch of calculations to get the planet to be in the right spot. And that's just, we're not going to demand that of one of these planetary minds. I think he says that in that chapter. So that error, I think, means the overall idea of even, using an epicycle, letting it move in a circle that way. Yeah. But I'm not sure about that. I know he comes back to it in chapter 50. He talks explicitly about this problem, but it's just not coming to me right now. The specific thing about C and F. So I think we'll come to it. I tell you what, if it doesn't, I think that'll come up, or definitely should be able to be answered in the class next week, because this is it gets further resolved in chapters 46 through 50. He says more about what this problem is using different language, but he's still addressing the same thing about getting bunched up at the apsides. So let's see if these future chapters clear it up by talking about it in a different way. Well, yeah. I guarantee we'll get to it in chapters 46 through 50.
Okay.
It's because it's all right. Just to say a quick thing, I don't want to get too far into it because we're definitely it's the class next week, so we'll be talking about it anyway. Let's see if I got a good picture here. The Kepler. Okay. Well, it's a whole thing for next time, and I don't want to get into it because let's stick with what we've gone through in the classes so far. We'll talk about it next week. I promise.
Yeah.
Anything else? And people watching on YouTube, if you add, let me go on to the, possible you've been adding questions on the YouTube page and I haven't seen it, so I'm going to log into that too, and let's take a look. People on the Hangout, feel free to speak up. I'm just checking here. Okay. Anything else?
We have a hunch on
Uh-huh.
what the answer to our question was. Give me a second to pull up the animation. I'll be right back.
Okay. And after that, if somebody doesn't, still please do ask something. But I know that there had been a I talked to a lot of people about the uncertainty and the eccentricity in back from part 2. So talk about that after what Ben's got here. I can report on another question I got. Let me just recount the, because I got on like Hangouts with just about Hangouts or phone calls with basically everybody over the past week, and a question had come up somewhere asking how are opposition observations made? Because that word achronical, which means rising at night, like right as the sun is setting, Mars is rising. That's when things are in opposition. Seems like a hard time to observe a planet when it's down at the horizon, it's a very bad time to observe a planet. You have a lot of refraction. And Kepler, he had theories about refraction, but no one had really figured out the right amount to make adjustments exactly. When oppositions happened, it wasn't because you actually used your eyes to know that they were in opposition. Especially since Tycho was using a fake sun anyway, he would have a table of where the sun would be. And when he saw Mars in the zodiac opposite it, that's how he would figure out, when opposition was. So one night he sees Mars in a certain place. He looks in his table of where the mean sun would be. There's a certain difference, 179 degrees. The next day, the difference is 181 degrees, means that right in the middle was opposition. So. All right, did you find that thing, Ben?
Yes. So I'm looking at the animation on the website for 45.
Okay.
And it's the one that has the blue circle, black circle, and red dotted ellipse. So on that black circle, imagine 2 dots near each other.
Let me put this animation up for people to see it. Okay, go ahead.
Hold on. Okay. So on the big black circle, imagine 2 dots that are pretty close to each other. They could be anywhere. And draw a line from one of the dots to B, and then from the other dot to B as well. By doing that, you would be marking off a segment of the black circle and a segment of the ellipse. And you'll notice that near aphelion and perihelion, those segments would differ the least. In other words, the crescent is the crescent diminishes to nothing between the ellipse and the circle.
I see. So between the I don't know if you can. I got my cursor on. I don't know if it's even visible. But like over here at the quadrants, say over here on the left. Oh, I can point at the TV. Like
Yeah, okay.
Yes, exactly right. Yeah, you exactly got it right. Yeah, over here the difference between the two. If you're watching, you're watching a certain amount of arc along the oval and the circle. It's not a very big difference between their lengths over here. and it's much more exaggerated up here. Yes, that's right. And that's actually, I'll show you a picture that illustrates that from chapter 59. Let's see. I guess that's maybe the best one. No. Yeah. Yeah, here we go. You can see that. The difference in distances here becomes nothing right at the quadrants, and then the distance for certain amounts along the arc here. This is where the shortness of the oval makes itself most pronounced at the apsides. So that I think that's why that quote you had read there, that the distances that get accumulated near, yeah, they get accumulated at the apsides because moving. Because that's where the oval gets shorter than the circle is at the apsides. So it would seem to get bunched up there.
I think it's a little bit different. I wish I could. Maybe I can draw over here.
Here, does this work?
Can you guys? I don't know if this is gonna work.
It might. If you can use a marker instead of a pen, the line might be too small with a pen there.
I mean, this might be a way of. I'm not sure if this is going to agree or disagree with what you said.
No. It's going to seep through that page.
Oh, right.
It's just this.
You're off camera right now. I mean, as long as you move it later, I'm just letting you know that you're off.
Oh, yeah. Let me draw it real quick, and then I'll just point to it on the camera.
You can just lift it up, I guess.
Now I gotta. Wow, this is like.
Higher. Perfect. Great.
So these lines mark off a chunk of the circle and the ellipse
Right.
in both cases, and I would guess that over here they're pretty close to the same. Over here they're not.
Right. That also sounds reasonable, and it's the opposite of what I said. So that's funny, and they both seem to make sense. Well, so the picture I showed was from 59, so it's out of order. It's using an ellipse.
But they're marking off equal arcs, right? Equal time arcs.
No. Yes, they're equal. These are equal because they're equal arcs on the epicycle. That means yes, they're equal time arcs, right?
Looking at the animation, not that one.
Oh, right.
Imagine that the red dot had been the black circle, and then we bent it in. So we changed it the least at aphelion and perihelion, and we changed it the most at the quadrants. That's where the arc has undergone the most bending. Or that's kind of misleading to say it like that. The arc of the red and the arc of the black is overlapping at aphelion and perihelion. Forget the whole bending.
Right. I just feel like it's really best to come back to this one. I mean, I think you might be right, but he's going to build on this specific objection for like 5 more chapters. I mean, it's not the subject of all 5 chapters, but he's definitely going to keep coming back to it. So I say, see, after we've read through up to chapter 50, let's see if it clears it up. Right.
One thing that occurred to me the other day, and you can tell me if you think if this is going in the right direction, is when he disproves something and then brings it back, such as an equant or an epicycle. In other words, he revolutionizes the ideas slowly. That made me think of the moment in the Parmenides dialogue where Parmenides says, well, there's this exercise you have to do. And Socrates says, well, what is it? And he says, well, you have to imagine all possibilities. So take your argument, switch one thing, and see how everything else responds, and go down the line with everything. Only in Kepler's case, he's not doing that exercise with everything, but only what changes according to seeking physical causes. So as he seeks a physical cause and tries to apply it, tries to fit it in there, he'll change one thing and then see how things respond and then bring back old arguments. Even though he knows they're probably not true, he wants to see how the puzzle reorganizes itself.
Mm-hmm. Well, yeah, I don't know how generalizable that is. I mean, one thing's for sure is that all the terminology changes meaning a few times in the book. One of the biggest examples is eccentric anomaly. Eccentric anomaly's got a very clear meaning in the with an equant, it has a center. With area time and the circle or whatever, there's a center. There's an eccentric anomaly. It means something. What does the eccentric anomaly mean? Let's, if we didn't have this epicycle or whatnot, but jumping ahead, just the general idea, if we got a planet moving in an oval of some sort, the sun's not at the center. What does eccentric anomaly even mean anymore if there's nothing special about the center? I mean, there's nothing physical at the center of a planet's orbit. Later, Kepler is going to say, I don't even like the idea of the planetary mind or physical cause or anything, even having anything to do with the center at all. If he can eliminate the center altogether, that's going to make him very happy. And the eccentric anomaly goes with it. So, yeah, the meanings of the things differ. I mean, when he brings the equant back in part 3, it's not because he's giving it another shot. It's because, it's for a different. It's for a different polemical purpose. He's got to get rid of that objection from the Mysterium about the planet moves at different speeds, but the sun ignores that idea. Then can't be an idea. He said, I think in chapter 32, he says, he said, in my Mysterium, I postponed arguing this physical case about the cause of the Ptolemaic equant for the sole reason that it could not be said on the basis of ordinary astronomy whether the sun or earth uses an equalizing point and has its eccentricity bisected. So he's doing it to make his metaphor, his physical thing universal. He's not really giving he's definitely not giving the equant another chance as the old form of equant. He's already thinking that the equant's needed for the physical power to have some meaning, and he's bringing it to the Earth. Anything else? This might be a question. This isn't just being totally rude here. Well,
Just one point of clarification on the on chapter 41. When he basically starts to do the observations of Mars from the Earth, um, he's taking the distances from the Sun to the Earth as defined by the new orbit which he constructed around the previous observations of the Earth from Mars, and the relative distance from the Earth to the Sun relative to the distance of the Sun from Mars. So he used sets of those observations to create a new orbit. And then, so in chapter 41, he basically is taking that orbit and he's going back in the data book and selecting days which are one Mars year apart from each other. And then simply he's doing a similar kind of calculation again, but this time to find the distance that Mars is from the Sun, with the idea that now the distance from the Sun to Earth is now defined, since he knows he has this new model with the bisected eccentricity and and the apparent Sun as being, and the distances from the apparent Sun being defined. So, that's the general idea, right?
yeah, I think so. I think I see what you're getting at. That yeah, he's in chapter 41. He's definitely counting as back in part 3. He had held Mars still to watch the Earth. That gave him an idea of the Earth's orbit, and he felt confident with this bisected eccentricity. And so coming back to this point in the book, okay, so he feels comfortable using these Earth-Sun distances, and then he uses them to define the these Mars distances. This business of you got the Earth in the same Earth in different places, watching Mars in the same place. Yeah, he's using these Earth-Sun distances as a given for that. Here's the thing: he knows the Earth doesn't move in a circle around the Sun. So, if he does this to get a Mars distance, he kind of knows it can't really be right because the Earth also isn't a circle. So all the Earth-Sun distances aren't actually quite right. So it's a sort of thing where he needs to. He actually has to come back and redo everything once he finally figures out that planets move in ellipses. Then he would be able to come back to these earlier chapters with a better idea of Earth-Sun distances, and he could then recalculate the Mars orbits and get a very final idea. So some of that work that he did of then cycling back through and redoing everything with his final idea of the planetary motions, he doesn't do that in this book, but he certainly did it before he put together the tables, the Rudolphine tables. So.
Right, yeah, and then at the end of the chapter, he, like you're saying, goes through how if you actually do this and find these Mars distances this way, you're going to discover that you're actually finding sets of distances which imply completely different circles. So, but I was just one question that was on my mind was kind of the way in which he was determining these different Mars orbits, because in in all the previous calculations he was using 100,000 as the distance. But now the Mars orbit isn't what he's taking as known. He's taking the Earth distances as known. And so if he's taking a set of Earth distances as known, and then looking at another set of Earth distances, he would only have those values as they related to the distance of Mars at that point. So then he would have to use his orbit as the tool which enables him to correct the distances to find the distance from the Sun to Mars as being of a different value than just 100,000, which he used for all these different sets. You see what I'm saying?
I think so. Or I mean, there's certainly a reciprocal thing between finding the one, and then that would change how you then look back at the other. But I think you're saying something more, but I'm not sure if I'm understanding it. Is that? I think that's part of it, right? The reciprocal thing, or?
Well, like for example, if you had one set, if you wanted to obtain a set of 3 different distances from the Sun to Mars,
right?
That would, and you took the distance from Mars to the Sun as given, say 100,000, and using your trigonometry to find the distances, those 3 distances from the Sun to Earth, and they're all slightly different. From those different distances, you can construct a circle, and you can find where the Sun lies in that circle and where the center of the circle is. But then you have another set of, you do that again for another set of Earth-Sun distances, and you use, once again, you just use 100,000 for your Mars-Sun distance, and now you're finding, again, more distances from the Earth to the Sun relative to Mars distance. But obviously the distance, those distances from the Earth to Sun couldn't be those that you calculated relative to Mars, because in this new position that Mars is in, the distance of Mars has changed. So how do you adjust these new Earth-Sun distances? You'd have to basically use your orbit which you constructed, use the orbit which you defined to adjust that new set of 3 distances that you took that you calculated of the Earth to the Sun from, with reference to a new Mars position. Is that a little bit clear?
I think so. I think it. Let me say back. Here's what I'm hearing.
Yeah.
When we use one Mars position to find out where the Earth is, to figure out where its center is and create an Earth orbit, but then Kepler does that using another Mars position and then another Mars position. In chapters 26, 27, 28, he uses 3 different Mars positions. So each of those Mars distances from the Sun is different. He also, I mean, he knew they were different. You know, Kepler knew they were different back then too. But how is he then supposed to figure out something specific about the Earth's orbit when he's not certain about the Mars distance? How would he have any certainty? How could he make conclusions about the Earth's orbit? Is that it? Is that what you're?
No, I'm just trying to. I think I got the idea in my mind of what I'm thinking, but I just having trouble communicating it. Basically, what I'm trying to convey is my understanding of how Kepler would have obtained these different distances from the Sun to Mars using these different sets of Earth, Sun, Mars angle relations. Because if you were to go back in the data, and he had and he had, 3 sets, or a set of 3 Earth positions, which were all 1 Mars year apart, but with respect to a different Mars position than 3 other Earth positions, then he would just use the Earth distance as the thing that was defined on the basis of the orbit he constructed in order to figure out this new Mars distance. If it's not clear, it's not really a major point. It's just, I was just kind of going through my mind of how he would actually, like, if I actually was sitting there and I had like the data book and I wanted to actually do what he did, I was just trying to think in my mind about how he would. And basically what I'm thinking he would do is that he would take, let's say he had 2 sets of 3 Mars, Earth, Sun angle observations. And for both sets, he used the Mars-Sun distance as 100,000 and calculated the Earth distances based off that. So if he were to take just one of those sets of 3 Earth-Sun distances, he could construct a circle. Now, when he were to look then at the second set of Earth-Sun distances, he could basically compare just one of them, one of those values, with the value that would be implied by the new orbit which he created. And on the basis of that ratio, he would change the Earth and the Mars-Sun distance.
I don't understand you, to be honest.
Maybe when I'm down there for the event, we can go over it or something.
Okay, yeah. Well, I think being able to actually share paper and stuff would help. So it's tough.
In the same room might help. Yeah.
I'll be honest, I'm really not that, I mean, I didn't read back through those. I mean, Megan might have a better idea about that than I do. I haven't read back through those chapters recently. In other words, I'm not actually that, I don't really have a very real living sense of what he actually did in 26, 27, and 28. And now that you're talking about it, I'm kind of thinking, wow, there's really no way to go. There's no way not to make it, you have to rely on certain assumptions as you go along the way here, as you're moving forward. And you don't really have any certainty. Here's the thing, he doesn't have any certainty for quite some time. I mean, he keeps relying on Tycho's this, he relies on the general size of the Earth versus the Mars orbits, etc. And, it's sort of, you have to sort of keep coming back to everything with the advancements that you've made and then keep rethinking all of it. Because up to this point in the book, really nothing that he has done has been exactly right. I mean, the eccentricity of Mars, which he gets so carefully in chapter 42, he doesn't really know that that's right, because it's using these Earth-Sun distances, which he kind of actually cheated, and when he got the Earth-Sun distances in the earlier chapters, he was using a kind of an oval or something. Donahue got a footnote about it, that he wasn't really using a circle. So, it could be that these things are written a little bit the chapters are a little bit out of order, but he certainly didn't know, he didn't have the Earth moving in an ellipse when he got the distances. So, it's sort of tough. He doesn't really have anything firm to stand on yet. He has things that are relatively firm enough to make a point about where he's got to keep going. But even this eccentricity in 42, which seems very certain, isn't completely so. Although the Earth's eccentricity is not that big. I mean, in other words, the Earth doesn't differ from a circle very much at all. The difference is it's pretty darn slight. So it's not going to. In fact, I'll tell you. I mean, the amount that the Earth comes in from the side is. Let me just. Oh, hey, I'll do it on that piece of paper. Just to show it. We'll do that. Where's that thing here? Using the Earth's eccentricity of 1800. Let's take a look here. I mean, this is cheating and using the, saying we know it's an ellipse and all that, but get a sense of the size. Here's Earth's center. Here's the sun. 1800. The way it works in the construction of an ellipse, over here, instead of actually being 100,000 away, the way he makes the ellipse, this distance would be 100,000. And, it comes in a little bit. So just doing the Pythagorean theorem here, we would take the square root of 100,000 squared minus 1,800 squared. Now let's see what we get here. Square root of 100,000 times 100,000 minus 1,800 times 100. We get 99984 instead of 100,000. So the difference is only 16 out of 100,000. So that's the maximum difference of the that's the maximum difference of a circle. That's the maximum difference of the Earth's distance based on it being an ellipse instead of a circle. So given that's that small, Kepler didn't know it was going to be specifically that small, but he's sort of got some idea already that the Earth isn't moving in a circle, and he says so in those chapters in part 3. But it's really not enough to change what he got in chapter 42 that much. Although he will end up redoing all of this before making and publishing the tables and and all that. So okay.
Okay.
Well, I'm going to turn this YouTube off now. So if you've been watching us on YouTube, still, I'll keep an eye on this. If you have some questions, if you watch this thing with all of the pauses in it, congratulations. And if you have any questions, you can add them into the comments there, and I'll get back to you.